Hi, good morning or good afternoon or good evening, wherever you are. I'm Jean-Louis Van Belle. Um, I'm a bit of an independent researcher, and I look very much into interpretations of quantum mechanics. I've published a lot on quantum electrodynamics. That's sort of the theory really of electrons and photons and how they interact. And I think we found sort of a realist interpretation of quantum electrodynamics. But today, I want to talk a little bit about quantum chromodynamics. So quantum chromodynamics, that's sort of the sector in the standard model that looks into, what goes on inside of the nucleus. So we're not talking about the electromagnetic force anymore, where we're talking about what is called the strong force. And we're also looking at decay. Decay is often referred to as the weak force, but I prefer to talk about decay because decay it's not really a force, right? And then a weak force is a bit of a contradiction. So let's say the strong force and decay processes. So that's what my talk is going to be about today. Quantum chromodynamics, comes from color and the color rule basically. This is sort of what probably you've seen many times when you Google, when you do a bit of research. It is supposed to show what goes on inside a nucleus according to the standard interpretation, the mainstream interpretation of quantum chromodynamics. Basically, we have a proton and a neutron inside, and a nucleus, and we have probably more protons and more neutrons. And then the whole theory is actually that there are these virtual particles, which are referred to as pions here, and a pion basically, mediates the strong force that keeps the proton and the neutron together, or that keeps two protons together. Why is it a strong force? It is a strong force because, if you have two protons, two positive charges, they will not attract each other. They will repel each other, and very strongly at the distances that we are talking about, so like 1 femtometer. So you need a force that is much stronger and than the electromagnetic force to keep the particles in the nucleus together. And so that's what the strong force does. The strong force has a shorter range, so it actually falls off much more rapidly than the inverse of the distance. The electromagnetic force will fall off with it will fall to the 1 over r rule, the potential. And the Yukawa potential has another factor. We're not going to go into the detail, but so the strong force basically is in the orthodox interpretation, the mainstream interpretation, is mediated, as they say, by these gluons, or virtual particles, pion here. And it's a bit of a funny theory, because you see that we have these quarks inside the proton and the neutron, and then a U quark and a D quark. And these quarks in standard theory have a certain mass or a certain energy, and they have a certain charge, and they have other properties like spin. They're fermions, spin 1, 2 particles. At the same time, in the standard interpretation of quantum chromodynamics, they switch color all this time. So the color charge is, for some reason that I don't quite understand, and we'll talk about that, is sort of, they swap colors all the time. So the color charge is not considered to be like a permanent property of these quarks, and that's actually where I have a bit of an issue. But yeah, look at this a little bit and think about it. Think what is going on here. We have basically white. How can you make white? So the theory is that actually baryons will consist of 3 colors, and the 3 colors together need to make white. So that's like color television. Color television is works with red, green, and blue um, light diodes, and they mix, and you can mix these colors. And if you know anything about programming, then you will have white when you mix red, green, and blue in exactly the same proportion. So that's RGB color 255. 255, 255, or hex code FF, 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 so in the hexadecimal code. If it's slightly off, you won't have white. For instance, Snow White, which is not exactly white, is RGB code 255, 250, and 250. But so in quantum chromodynamics, you can't have a color that's off or that's not. It needs to be white. So you can also make pure white by mixing a color and an anti-color in quantum chromodynamics. So green and anti-green also makes white, and red and anti-red, and blue and anti-blue. So the pion, or that virtual particle that's being exchanged here, also makes is white. So that's where it's a viable particle in quantum chromodynamics. Particles come in two varieties. That some of them are like permanent fixtures, like a proton and a neutron. They don't decay, or well, proton is very stable. We haven't seen proton decay. We have seen neutron decay, though. Neutrons do decay when they're outside of the nucleus, and they decay actually sort of like they have a lifetime of about, an average lifetime, a mean lifetime of about 14 minutes and 41.5 seconds. So yeah, in less than 15 minutes, they sort of decay if they're outside of a nucleus. And protons, in contrast, they're stable as far as we think. And then all the other baryons, as we call it, baryons are particles that are made up of three quarks, according to the quantum chromodynamics. They decay much faster. Like these pions here. They have a mean lifetime of about 26 nanoseconds, the charged pions, because we have a positive pion, negative pion, neutral pion, and neutral pion that sort of is much less stable, that sort of dies off in a few nanoseconds, really, about 884, well, attoseconds, sorry, it's even worse than that. So that's 10 to the power minus 18 seconds. So that's really like, you wonder, can we still call that a particle if it sort of decays so fast, if it falls apart so fast? So that's something you need to think about, and we'll talk a little bit about that. But that's the principle here. So that's what you see happening here is the quark-gluon model, and that's the mainstream interpretation. We will sort of try to wonder if there's nothing simpler than that, because it looks funny, and according to me it really is a bit funny. So you know what is quark theory? When Gell-Mann came up with it in the beginning of the 1970s, they had this particle zoo, as they call it, in these atom smashers, or what you want to call them, the colliders, proton-proton, or leptons firing electrons into protons, or in nuclei, or alpha particles. They found this whole zoo of particles, as they call it. But again, these are most of them are really very, very short-lived. I mean, almost all of them, except the proton and the neutron inside of a nucleus, because the neutron, even outside of the nucleus, will also decay. So these particles, if you can call them, they're not permanent fixtures, and we'll say a few things about that. But they needed to organize that zoo, because we have about 140 mesons, and so that's where then they came up with this quark theory, that they said a proton will consist of U and D quarks and a neutron as well, and we can mix them, and that's sort of where these quantum numbers come in. And then they found that there's not only U and D quarks, we also have a strange quark, and a charmed quark, and a bottom quark, and a top quark, heavier quarks, lighter quarks. I mean, in total we have 3 generations, 6 quarks in total, and we use that to classify the mesons. We have these light, unflavored mesons. The pion here, as you see it, the P plus or P minus, or the P0, and then you have the heavier ones, I mean, that have a strange quark, and so that quantum number will sort of lead to the strange mesons. And then we have the charmed strange and the bottom mesons, and so we actually use these quark property, as should we say it? I mean, it's a particle, but at the same time, you know, the particle itself is used as a classification, as a property to sort of classify all these mesons. We will come back to that because we think it's a little bit an hoc theory, and maybe we have, you know, we have so many quark numbers, quantum numbers, sorry, and we also they also invented sort of, well, invented, they defined an isospin number, and then of course you have quantum numbers that you know from quantum electrodynamics, you know, the spin and the angular momentum. So a lot of quantum numbers in quantum chromodynamics, much more than in quantum electrodynamics, and that's where the theory is sort of feels a bit weird. In baryons, we have even more baryons than mesons, and here I have that list of the QCD quantum numbers, the quantum numbers you use to classify all these particles, you know, isospin, angular momentum, the parity, sort of a symmetry, you know, and up quark, down quark, you know, your list of quarks. Yeah, of course the electric charge is there, then there's the baryon number for baryons, and then actually, you know, we see whether, you know, baryons are made of 3 quarks, but then, you know, it can have a strange quark, but it can also have a property which is called strangeness, and a property which is called charm, which is quite separate from the fact how many charm quarks it has. And then we have bottomness or beauty. So a lot of quark numbers, and sorry, a lot of quantum numbers, and yeah, that feels a bit funny. You would think this sort of, is there no more fundamental theory in terms of you know, what happens, some kind of conservation law, or no, we just have these numbers that you know, classify the baryons and the mesons. And then I put a standard model of elementary particles there because, you know, these are the big questions that you have. Why are there 3 generations of quarks and leptons also? We have the electron, the muon, the tau, and is there sort of no? And then the thing is that it's very typical is that, you know, we suppose in quantum mechanics that, you know, forces are mediated by gluons, by photons, by bosons. And these are virtual particles. We're not talking a real photon in a light beam. No, we're talking about, you know, the 2 electrons that attract each other, or sorry, well, a proton and an electron that attract each other, and they're supposed to exchange virtual photons. Which I think is actually, you know, it's like ether theory in the 19th century. We've never seen these virtual particles. Can we really like prove them? Do we need them? That's a bit a question. In quantum field theory, of course, you know, that's the standard interpretation. Do we really need quantum field theory? That's a bit the underlying question here in this presentation. So to get a bit more familiar with what we are talking about, I've jotted down 2 equations, 2 easy equations that in quantum chromodynamics. One is the decay of a neutron. Said that the neutron is actually, you know, it's stable inside of a nucleus, but outside it will decay, like, you know, 11 to 14 minutes, sort of. The mean lifetime is 15 minutes, 14 minutes and something. It will decay into a proton, and in the process, you know, it will eject an electron, so you have the charge conservation. We had a neutral, so 0 charge neutron, and then it sort of disintegrates into a stable proton. A proton decay we don't see, so we have a proton is a permanent fixture in nature, and then the electron is also permanent, and then we have sort of, because of the energy equation, the energy conservation, I should say, we also have that neutrino. That sort of makes up. It's like in these equations, it's like money. You know, you need big denominations and small denominations, and, you know, banknotes and then some coins. Neutrinos are special because they're light. They have very little energy, and so you would think that oh, why is there no photon there? Because a photon is very useful, you know, as change in that when we talk money or energy conservation. You know, a photon, you know, can range between anything between, you know, few electron volt or 0.1 electron volt to gamma rays. Gamma rays can, you know, are in the mega electrovolt range. So photons are very useful to sort of, you know, make sure that the energy is conserved, because they they can have all kinds of energy, and so yeah, then the left and the right hand side will be equal. But no, here we have a neutrino. A neutrino is light, doesn't have a lot of energy, but it always pops up when there's decay processes, neutrinos. So neutrinos are a bit mysterious, and they have something to do with the weak force, with decay processes. We have another below there. We have a pion. So pion is a meson, consists of two quarks in the theory, and that sort of disintegrates into a muon. So we have a positive. If we have a positive pion, it will be a positive muon. And there again we have a muon neutrino. You can see there the symbol for a neutrino, but with the mu as a subscript, so it's a muon neutrino, a lot heavier. And well, what happens with that? It sort of, well, it has more energy. It's heavier mass. So the muon itself, the mu plus, is not stable, and that's going to disintegrate then into something that is stable. Well, stable, a positron. Is the antimatter counterpart of an electron, so that would be stable if our universe would consist of antimatter. Antimatter is just matter with opposite charge. So in theory it's stable, but in practice, it will run into a normal electron, a negative electron, and it will disintegrate. You get a big flash, a big two photons. Two photons. Why? Because of the spin rule. And then, yeah, that's the disintegration process. So a pion falls, becomes a muon. The muon becomes a positron or an electron, depending on the charge of the muon. And then we have another neutrino and another muon neutrino. So you see here I have an anti-neutrino in the first. So the bar above the neutrino symbol it means antimatter. So a big question is actually, what makes what is the anti-particle of a neutrino? Aren't they the same? For practical purposes, they're the same, actually. If you look in the literature, they say, well, an anti neutrino has opposite spin, but antimatter really means electric charge. So this is sort of one example of a bit of a poor definition. For all practical purposes, neutrinos and antineutrinos are the same. Opposite spin is opposite spin. I put a table down there that says, let's try to sort of see those decay times and see if we can make sense of it. So I put an electron there. It's stable. Its lifetime is infinity, and that's its energy is about 511,000 electron volt. So we measure an electron volt because we're talking small stuff. The Joule is a big unit for energy. So what we could try to do is, the theory is a bit that stable particles like electrons and protons, they we will think of them as some kind of oscillation of a charge, and that oscillation, will be permanent, because it will be like, that's the Planck-Einstein law. It will be an exact integer number of Planck's quantum of action, h. And so yeah, if you multiply the energy and the lifetime, we'll have infinity. So if we measure that amount of physical action, because energy times time is physical action, then there will be infinity. But for muons, pions, and I put there a tau particle, sort of a very really heavy lepton, you see the energy is much larger for these things, and the larger the particle, the more mass, the more energy, the shorter its lifetime in general. And that's kind of funny. But if we then look, we multiply the energy and the lifetime, do we get some fixed value? Or no, we don't. We just see that it does diminish. If we look at the energy times the lifetime, and we say that that's a certain amount of physical action, and we think of it as an oscillation, then we should think of it as a transient, an oscillation that really dies out. And the funny thing is, the heavier the particle, the more energy it has, it dies out a lot faster. So you can think of sort of, if you think of the h as the action that you associate with one cycle of an oscillation, and you will see a muon has a lot more cycles in it than a tau particle, about 10,000 times more. So but yeah, that's sort of a general rule. It's not easy. You can play with these things and you get all kinds of interesting graphs, but it's sort of an intuitive rule that is very hard to quantify. I've tried, but you don't get all that much out of it, except that general rule that particles that are really heavy and have a lot of energy, these third generation particles, they just die much quicker, and they are like resonances. So let's. This is the standard theory as I presented it. I want you to sort of, when you think the color charge is special. Now, if you think mass of a particle, gravity, it comes like in one color, right? We have big masses and small masses. They're positive. We don't have negative masses. They attract each other. In electromagnetism, it's different. We have like two colors, plus or minus, right? Positive charge, negative charge. +3 and -3, or +3 and +10. So we have two types of charges, negative and positive ones. And you could say sort of in quantum chromodynamics, it becomes even more complicated because we've got three types of charge, really, red, green, and blue. And we could quantify that. We measure electric charge in Coulomb. Maybe the blue charge, red charge. It's gonna be something different. Maybe X Yukawa or X Einstein. We need to invent a unit there. There is no unit for that. We just call it. We just have these three types of charges, but we don't try to. And that's one of the problems I have with mainstream theory. There's little in terms of thinking about how would we quantify them. We can think of three types of charge, but what's the magnitude of these things? And I'll talk about that. The slide here basically shows that the first impression is really that we can't see, in physics we can't solve the gravitational three-body problem, the three-body problem as it's called. There's this gravitational attraction between three stars or three planets. If they're sort of and if their order of magnitude of the mass is the same, the system will become chaotic. You can see that on the left-hand side. But there is a special, and that's probably the way we can think about the strong force in the nucleus. If it's called the elastic three-body problem. So then you have one color that gets, and its opposites are the two other colors, and they attract each other, but they do it in an elastic way. The forces, you see the force line there, and then it can move, and the system is not chaotic. And so that's actually a way to sort of think about these three types of forces. And the red, green, and blue. It's not a chaotic system. It can't be, because otherwise, you wouldn't have a good theory. So here again, I sort of want to. What intrigues me really is that in the quark-gluon model, the standard, we really have that mix of concepts, really. We have 6 quarks, and well, a lot of the particles we can model just with 2 quarks. The up and the down quark, the U and D. I think up and down is very confusing because we use up and down also for spin, which is something entirely different. But yeah, and we may think. I mean, what I put upstairs is just like let's separate, the properties and then sort of the carrier of these properties. I will call that a parton. A parton is a term that was coined by Richard Feynman in 1969, and he was sort of he said, okay, fine, if we're gonna acknowledge that we have like point-like constituents of matter. He didn't use the term quarks at the time. He said, let's call them partons, sort of a generic term. And at that time, he said, well, partons, what can they have? Well, they can have an electric charge. That's sort of probably what defines matter. It's electric. It's not electrically neutral. Even in a neutron, a neutron is made up of these partial charges. 2/3 and -1 or 2, -2/3, or 2 times -1 and 2, and then one d quark with 2/3 charge. And then we have the color. So basically, if you think about, in the nucleus, we have two kinds of charges: the electric charge and then the color charge. And we would have 12 partons, a red 2/3 particle and -1/3 particle, red, in three varieties: red, green, and blue. So that's really the idea, that partons are constituents of matter, would be constituents of matter with two kinds of charges: an electric charge and the color charge. And they don't switch. They don't change colors all the time. You will say, but yeah, that's a lot of partons. The quark model must be simpler because we only have 6 quarks, or 2 or 3. Most of the matter is made of the lighter quarks, the first generation. But when you think about it, it's actually not true that the quark-gluon model is simpler, because we have the gluons that sort of explain how these quarks change color all the time, because they exchange these gluons, these virtual particles that mediate the strong force. And for that to make sense, we indeed need to swap these colors all the time, send them around. And so that's actually a very, very funny model. And when you think of it, we have 12 partons in our parton model, 4 charges and 3 colors, so 12 partons. You may say quark theory has only 2 quarks, but that's actually not true. They have 6. And then also they have their anti-quarks, of course, and the anti-quarks, and then we have these gluons. So in the quark-gluon model, for the first generation of quarks, we already have 2 quarks, 2 anti-quarks, and 9 gluons. So that's 13 different mathematical objects, I would say. And if we just combine the electric charges and the color charges, we have 12 objects. So the degrees of freedom in the simpler parton model, that doesn't rely on the exchange of virtual particles, is has the same, or even less, 12, 13. It doesn't 13 instead of 13 objects. We'd have 12 in a parton model. So that's interesting. Why do I mean, the two models are really actually equivalent from a bit of a scientific or philosophical or epistemological perspective. We have these two theories would work. Either we have partons with a permanent color charge and an electric charge. The quark-gluon model, relies on this exchange, but the degrees of freedom is the same, or if actually, the parton model is a bit simpler actually than than this parton model, the original parton model. So can we work with that actually? I mean, the question here really is that can we explain these 140 mesons and these and all those different resonances or transient particles with a parton model? Well, I'll talk a bit about that. At first you would say, no, we don't have enough degrees of freedom here. We have, if we look at the strong force, probably what we would have to do, as I talked about assigning some magnitude to this force. A red and a red parton would attract each other with a certain strength. I put the S for strong or strength, and so we would have a coefficient there, a red strength of the force, and then between red and green we'd have a certain strength. Of course, that would need to be the same as the strength, the magnitude of the force between green and red. Blue and red would have a certain coefficient. We need to be flexible. So we'd have actually a symmetric matrices there with 6 independent coefficients. And symmetric matrices are interesting. because they have all kinds of interesting properties. And, there's only 6 independent coefficients there, but there's other properties that you might think of, and it's like eigenvectors and eigenvalues. A 3 by 3 symmetric matrix will have 3 eigenvalues, and that's probably where you want to think in terms of those 3 generations that could come out of that. But in any case, we have 6 coefficients, and now we can combine it with the electric charge rule that says a real particle, we know that quarks and gluons, you have that confinement. We can't have partial charges. Any real life meson or baryon will need to have either 0 charge or -1 or +1. So it needs to add up. So out of these 4, if your particle A and parton B come together, we're modeling mesons here, 2 partons together make 1 meson. So then we have out of the 16 possible combinations, we have 8 that actually can are viable. So 6 times 8, we'd have like 48 possibilities, and you will say, well, we have a lot more mesons and neutrinos, so we need to sort of see if this parton model that we have here has enough degrees of freedom. We only have like 2 quantum numbers here, and then with these 2 quantum numbers we can only make, so to speak, or model 48 mesons, 40 in this case, because we're only looking at combination of 2 partons here. So that's not enough. But of course you have other quantum numbers then, the classical ones that from quantum electrodynamics, and that have when you think about an electron, we may think of it as some kind of a circular current. We have electron models that model that. I wrote about that, and then you can think, well, it has a magnetic moment, and the magnetic moment can be up or down. So then we have the spin quantum number, and if it's in an orbit around a proton, then we have an angular an orbital angular momentum number. So we can add these numbers as well here, because with electric charge, of course, if our partons carry electric charge, then they will also have a magnetic moment. So you can see we can multiply already 48 by 2, and we have a lot more particles. And then the interesting thing really is, and that's where there's no research or no creativity in quantum chromodynamics, is with the strong force. If there is a strong charge, just like with an electric charge, we may think of some kind of internal current, a red current, a green current, and a blue current. It sounds funny, but these are physical concepts that are perfectly fine, and you could work with them, and then you would have a color moment or a color magnetic moment. I mean, it's not magnetic because it's not the electric force, but we would have something similar. A red current, a green current, and a blue current would produce some angular momentum and some kind of moment, and we can have quantum numbers for that. So it's really very easy to sort of, based on this parton theory, come up with a physical like a more common sense explanation for all these various combinations that you have, these lists of particles, as I showed you, the particle data group of the CERN keeps track of all these things that we find. We find almost anything that is possible. And the thing is, this is a model here, the strong force combined with the electric charge rule, and then some inventiveness that actually is much simpler. And because we have so many QCD quantum numbers that it's honestly, it looks very ad hoc, and it looks very ugly. So I think that's about it, what I wanted to talk about. And so I'll stop here because this is already like half an hour that I'm talking. For further reading, I have the references here. So I publish actually on the site of Phil Gibbs. He's an independent physicist and mathematician. And so yeah, because what I'm doing is absolutely not mainstream. It's challenging. It's trying to be creative. And then I have 2 blogs, one on quantum electrodynamics, reading Feynman.org, and then I have one on quantum chromodynamics, reading Einstein.blog. So that's it for today, and I thank you for listening if you're still here, and well, goodbye and see you next time, hopefully.